So welcome to this seminar within the Road to CDC initiative. That is this initiative by the Italian chapter of CSS that try to foster involvement with the forthcoming CDC in Milan this year. I also would like to remind that there is an initiative for best thesis for master students and for the best for PhD thesis, there will be free registration to CDC. So I invite you, if you have students that recently graduated, to apply for this initiative. So it's a pleasure for me to have Andrea Carron here. That is a double pleasure because it was a former student of mine. He graduated in 2015. While he was a PhD, he also managed to travel first to Riverside, UC Riverside, then to Bingen, and finally to Santa Barbara. After he graduated, he went to McLaren, where he was having lunch with Fernando Alonso, which is not something that everybody has the pleasure to do it. And after a year, he moved as a postdoc to ETH, where he has ever been since then. Since 2019, he has been promoted to lecturer, and he's been working on different topics, mostly related to MPC. And in particular, today he's going to talk about MPC related to learning. So thank you again for coming here, and it will be a pleasure to hear your presentation.
Thank you very much, Luca, for the nice introduction. Okay, so it's really a pleasure to be here. Today, I would like to give a broad overview of some of the work that we have recently done in the field of learning-based MPC. Let me start with some acknowledgements. I'm the group of Professor Zeilinger. This is also most of these results are together many postdocs and PhDs and research assistants that are working in the group. So as a first, I would like to acknowledge all of them. And I also would like to start with some shameless advertisement about our hardware and software platform we're using. So you will see quite a few videos of experiments. We are mainly using these miniature race car that has been developed in-house. We're also using a miniature rocket. Is basically like an inverted pendulum where we control the thrust vector at the bottom, and an autonomous paramotor, or let's say a system with a parachute that where we can control the two lines. The miniature race car is actually an open source project. You can actually download from our repository all the hardware and electronics parts, and all the systems are controlled through the same software, which is also open source and you can actually use. Maybe to just give a few more details regarding the hardware. So these little cars are 1 to 28 scale, so they're 15 by 7 centimeters big. They have relatively fast dynamics. They achieve a speed of 5 meters per second, so slightly below 20 kilometers per hour. We have on board some computational complexity, so we have a dual core microcontroller. Communication is through Wi-Fi, and we have some onboard sensors like IMU wheel encoders and steer encoder, and the cost for producing one car is around $300. We also developed an indoor localization system. So in our lab, we use a motion capture that is quite an expensive option. And so we developed this, let's say, indoor localization system, which is much cheaper. It's based on a system used for virtual reality. It has an accuracy around 3 and 5 millimeters. And one single base station, which is this object here, can cover an area of 5 by 5 meters. You can daisy chain up to 16 of them. So you can, in theory, cover an area of 400 square meters. And one single base station plus the localization deck cost around $400 each. And then the code framework we use is a C++ code framework with a ROS wrapper around. And this allows for seamless transition between simulation and experiments. You can, if you're interested, you can find in our ETH repository, Git repository, all the, again, electronics, software, and firmware. Okay, now with this done, so what is the what are we interested in? So our research is in control of dynamical systems, and in particular in control of systems that are safety critical. What does safety critical means? It means that they are subject to constraints. You can imagine state and input constraints. And so here there are, we can imagine many examples. So again, the miniature race cars that I showed you before, where you, for example, want to stay within road boundaries, or you can think aerospace applications or other in manufacturing or industrial application. And the focus we had in the last year was about how can we, let's say, adapt our controller, safely adapt it and learn online. So this was, let's say, the main question, to try to understand where to introduce learning and how actually to efficiently and safely perform it. Now, before trying to answer some of these questions, let me try to bring a couple of tool sets that are needed. One is, as the title suggests of the talk, model predictive control. For who is not familiar with that, the idea of MPC is that we have use an optimization problem to find basically the control law. So we have an optimizer in the loop, and what happens is that we given a model of the system, we try to basically predict in the future for n steps the behavior of the system. We, for example, obtain a trajectory like this green one here. This trajectory, one that satisfies some objective, example, to progress as much as possible along the track, but at the same time to satisfy state and input constraints. So state constraints can be to stay within the road boundaries, and input constraints to don't exceed the actuation limits. And then, so we are given this solution, right? We solve it once and we obtain this green trajectory. What we do in order to introduce feedback is to just apply the very first bit and then re-optimize again. So repeat this operation, and this is called receding horizon. And now if we perform this, we obtain, for example, in this example, this vehicle, a behavior similar to this. Now, the other tool that we need is a way to solve the optimization problem of the MPC, right? It's potentially a nonlinear MPC. And the tool we use is sequential quadratic programming. So what we do first, we try to abstract from this MPC problem, and we think it as a generic optimization problem with a cost function and equality and inequality constraints. And we want to solve it. How can we do it? One approach is to try, first of all, to approximate this nonlinear program, this NLP, with a QP. And this can be done, let's say, if we have, for example, an idea on how the solution looks like, and in MPC, this is not a restricted assumption, and we'll see in a second, we can basically linearize our NLP around the current trajectory. And so what we do, basically, we linearize the equality constraints and the inequality constraints, and then we perform a convexification of the cost, where usually we have in the cost the gradient of the cost function, and the Hessian that is related to the cost function, but also basically to the Lagrangian. And usually this matrix M is also, let's say, convexified to make sure that the matrix M is positive definite. Otherwise, it's not very easy to solve this QP. And then that we have this QP problem, there exist many ways to solve it. We can use interior point, we can use active set, or our favorite method. And then we solve the QP. And then we obtain basically an increment from the current solution that we need to add to the initial trajectory we had. We checked if we converge with our, let's say, favorite metric for checking convergence. And then if we didn't converge, we repeat this process until we converge. Now, what are the advantages of this tool? Well, first of all, that is very easy to warm start. because you can use, for example, the previous solution obtained from the MPC problem as a warm start, and so that's why this first step is relatively easy. We need just to find the very first time a, let's say, decent solution, and then we can always use the previous solution of the MPC. We can also decide to perform, let's say, a more extreme version of this algorithm. This is called real-time iteration, RTI, SQP RTI, where we don't check about convergence. We don't care about convergence. We perform this loop only once, and we take the suboptimal, potentially also infeasible solution that we obtain. And there exist very efficient implementations available. One has been developed here at the University of Padova, which is MatMPC, but also, for example, Arcados developed at the University of Freiburg. And there exist also other variations. For example, if you perform RTI, you lose feasibility, meaning that you potentially don't satisfy constraints, which is what you want to do with MPC. And so recently we developed this approach called feasible SQP, where basically you perform this loop multiple times until convergence, but you fix all the first and second order terms until convergence. And if you do it, basically you can show that the algorithm will satisfy KKT condition, and so will satisfy constraints at the end. And with a computational load that is about 20% higher than SQP RTI, so still a very limited computational load, but with an additional guarantee. Okay. So if there are questions, please feel free to also interrupt me and ask. Now, in this domain, there are actually quite many challenges and, of course, also opportunities. And at the moment, we are looking at the domain of performance and safety, but also multi-agent control, multi-agent coordination. In this talk, I will mainly talk about performance and safety. Now, so again, the question is, how can we integrate learning into model predictive control? What can we learn, and what can we do with that? So the three things that I will show you are model learning. So we try to improve the knowledge of the dynamics. We try to be also to do cautiousness. So if you have any uncertainty information, we can perform, for example, constraint tightening in order to stay farther away from constraints. And also we can perform targeted exploration, always based basically on the uncertainty. But of course, the research in learning-based MPC is not limited to these three fields. Just to mention a few others, there is policy learning. So you try directly to learn the MPC policy with any approximator that can be a Gaussian process or a neural network. You can try to learn the terminal ingredients of the MPC, which are usually not very easy to compute, in general to compute. But also there are some other tailored approaches, for example, for iterative learning-based MPC. Okay, but let's start with learning the model dynamics. So if we keep the example of the race car, we can imagine we can model the race car as a dynamical system, okay, in this case in discrete time. And f of xu is the nominal model. In the example of the race car, for example, can be the bicycle model. And what can happen is that, for example, we don't describe perfectly the tire friction or the aerodynamic effects like the drag, and so we have some error. And so the second term defined with E is the model mismatch, also sometimes called residual dynamics. And then on top of that, we might have also some noise, some process noise that can assume, for example, that is Gaussian noise. Now here, let's say, plays a role of process noise. In a second, we'll start playing the role of measurement noise, as you will see. And now, so given this model here, that is, how can we learn the model mismatch? Well, if you assume we can either measure the state perfectly, or we can have a good estimation of the state, we can move the nominal dynamics on the left-hand side, right? And we can actually directly basically measure a noisy version of the residual dynamics. And that's why now this WK plays a role of measurement noise. And now the question that comes is, okay, at this point, this model is still very generic, okay, and not necessarily super useful. How can we model the residual dynamics? And we mainly explored two directions in the last years. The first one is to use, let's say, Bayesian regression for model learning. And the idea is that you model the residual dynamics as the product between some vector of parameters that are unknown, that we call theta, and some basis function phi that depends on the state and the input. And then how to obtain the basis functions phi. Well, now let's say that we call this the ML way, but probably when I was a student, we would have called it the standard way of designing the basis functions. We can use polynomial features. We can use Fourier features, so trigonometric basis functions. Actually, we have a couple of works on this, also from a former PhD student in Padova, Scampicchio. And or maybe trendy, where people can use neural networks to basically learn these basis functions. Or if we don't want to use, let's say, these pure machine learning approaches, we can either use directly information from physics or try to take inspiration from physics to get some of these basic functions. And this sometimes is referred as the physics-informed machine learning way. But basically, it boils down to if I have some sort of idea on how this might look like, how the basic function might look like, I just exploit this knowledge. And now, given the fact that we know the basis function at this point, or we were able to compute them, we can perform the parameter estimation, for example, using Bayesian linear regression. I mean, these parameters theta are linear. Or we can use Kalman filtering, and this allows us to also learn features that are slowly time varying with respect to the dynamics. And this can be done by assuming that our parameters theta basically behave as a random walk, where we can basically decide how fast they vary, changing the process noise in this noise W. And then the measurement noise, the measurement model is exactly the model of the residual dynamics, where we can realize that this model is basically linear as soon as we know the state and the input. And we can use our standard linear Kalman filter where the output matrix is time varying. Now, if here an example of how it works on some real data, you can see that we used here some, let's say, physics-informed basis functions that we're trying to mimic the Pacheco model for tires, and we can see that actually we can learn decently well the macro behavior of the error. Now we deployed these on hardware. Let me show in a slightly bigger video here. So we deployed these on both a drone and our little race cars. And in general, we can see that, well, not that maybe directly from this video, we can have, from the video, we can see we can have good performance. But in general, what we obtain is that we obtain better performance using by learning the dynamics. And we can start from let's say, worst learned model or identified model. Okay. This is one way to perform model learning. I told you that we look at two different options. The other one is to use Gaussian processes. And the idea is basically that we directly model the aerodynamics using a Gaussian process. And so the advantages is that this approach is non-parametric. Yeah, we select basically the kernel of our GP, and we are good to go. We don't have to select the features. It comes with uncertainty quantification. Of course, also if you use a Bayesian regression, we have a certain quantification. But let's say compared to using, for example, a neural network, we have disadvantage of having uncertainty. And it has been shown to work in practice, even though there is one big bottleneck related to the fact that the computational complexity of evaluating or updating a GP is actually very high, scaled cubically with the number of measurements. So quite a few tricks are usually required if you want to use it with a large amount of data. But we can see here that we have deployed it in our lab on two platforms, a robotic arm and Formula Student autonomous race car, but also in other labs have been applied to drones or to rovers. Okay. Okay, then we can also try to learn basically the dynamics of, let's say, of systems that are not directly controlled by us, okay? And for example, in tasks like manipulation. And what is important in this domain is to try to be able to generalize to different sort of tasks. So for example, imagine that you have a robotic arm that has either to open a door or maybe to lift a weight, or in general to perform similar tasks, but different. And so what we would like is to learn a model that captures the task structures, but at the same time is able to adapt quickly to the specific task. And as I mentioned, we try to apply these on a quadruped robots with a robotic arm on top to, for example, door opening tasks. And the idea is that we perform we use a parametric model as the one that I showed before with the basis function with the parameters. We try to learn some basis function that can adapt to different tasks. And then the specific adaptation is done with the specific parameters. And we can see here this in action. So on the left side, so on the top side, you can see the nominal MPC model. On the lower side, you can see the multitask MPC. And you can see with high friction on the door or with some human interaction. And in general, if I maybe play the video again, you can see that the multitask MPC behaves better, it's faster, is able to better reject the disturbances. And also, if you compare it to a single task MPC, here on this door that is attached with a lace, you can see that the robot with the multitask behaves in general better. Okay, now let's say this is about, let's say, model learning. Now I would like to cover cautiousness. So how can we can be cautious combining learning and MPC, which I think is really one of the nice advantages on top of learning the model. So what we can do is to not only propagate, let's say, the dynamics of the learned model, but also propagate the uncertainty over the horizon, and then use this uncertainty to perform constraint tightening, so to tighten our constraints such that we try to avoid constraint violation. This incentivizes a cautious behavior of the controller. The problem is that, of course, we need to understand how to propagate the covariance, which is everything but a simple problem. And also, we need to find a way to solve this MPC problem in a relatively fast way, because we are increasing the number of optimization variable by a large amount, because we add a number of optimization variable equal to the square of the state multiplied by the horizon. So the complexity increases quite a lot. So the proposed solution is always based on an SQP approach, but using zero order optimization. So what we do, we propagate the covariances using a linearized model. So we linearize the model and we propagate the covariance using the linearized model. And the propagation it's basically very similar to a prediction step in a Kalman filter. And so as a first step, we propagate the covariances. Then we perform the approximation of the NLP to a QP as done in standardized QP. And then we solve the QP, but we don't optimize over the covariance. So we fix the covariance, we don't optimize over. In this way, we reduce the number of optimization variable. What is possible, and then the rest is the same. So we have the solution, we check for convergence, and we repeat. The advantage of, so what we can prove in this algorithm is that we drastically reduce the computational complexity. But at the same time, if we let it run until convergence, we obtain a feasible solution that, of course, is suboptimal. And let's say, assumptions that are needed in order to basically have these guarantees is that we need a kernel that is quite differentiable. And at the same time, we need basically an uncertainty that is relatively small, which is probably the most tricky assumption to satisfy. The nice thing is that with this approach, actually, we are almost decoupling let's say, learning part and the propagation of covariance from the solving of the MPC. So we can basically integrate any machine learning toolbox, for example, GPyTorch, if you're using GPs, or Torch, if you're using other methods, inside the routine quite easily. And we can use, for example, GPU for performing the propagation of the covariances. And we obtain up to 1000 speed up with respect to a standard GPMPC approach that was optimizing over all the optimization variables and not using any sort of acceleration. Okay, and now just to show this in practice, so here we are now running on the race cars version process-based MPC, where we propagate the covariances over the horizon, but we are not, let's say, performing online learning. So the GP knows very little about the system, so we simply predict high covariances and will induce a cautious behavior. In fact, you will see that the car will move relatively close to the center line. You can see on the top right panel, you can see that the propagated covariances, and you can see that the car stays relatively close to the center line. In this way, for example, we can collect some data in a cautious way that we can use then to perform learning. And then after we basically train the GP, we can run again the same experiment now with a proper GP, and then we can see the behavior is less conservative. We perform a more, let's say, aggressive, we go on a more aggressive racing line. You can see also that the prediction has very little uncertainty because we became very certain about our model. And now this tool that uses zero-order optimization has been integrated in a Kados that is a toolbox developed at University of Freiburg, and it's available on the repository. And we're also working on open sourcing the learning burst version, not only the zero-order optimization part that will be called L4 Kados and should be available very soon. Okay. Now, for the last part, we want to perform, let's say, targeted exploration. And let's have a look at a problem, for example, of performing tuning of the cost of the MPC. In this example, in the example that I showed you, what we're performing with MPC is a path following controller, where we incentivize to progress along the path as fast as possible. But this is different from, let's say, performing racing, so to minimize the lap time. And performing the tuning such that the cars really goes as fast as possible is not an easy task. This controller is not super easy to tune. And what, for example, is done for a car if we change Carron, so we change slightly the dynamical model, we need to re-perform the tuning from scratch, which is a bit annoying. So the idea is that we would like to find a way to perform automatic tuning that also learns, let's say, basically from experience. And for doing that, we use this model that I showed you before, where we perform model learning, and the residual part uses basically intermodeling the parameters. Okay, and basically the learned parameters theta are identifying what we call context. So basically, if two different systems, they share the same theta, of course, also the tuning of the controller would be exactly the same because they're the same model. But as soon as this theta will change, we might need a slightly different tuning. And the way we perform now the tuning is that we drive lap and we observe the lap time. At the same time, we infer the context parameter theta from the data we collected, and we improve the model. And we keep driving and we keep measuring basically the lap time. And then we build a GP model that maps the current weights of the controller and the context to the lap time. So we try to learn basically this map. And then we use Bayesian optimization in order to decide where to sample the next point. And the way we use Bayesian optimization is by basically fixing the value of theta, given the current context, and trying to find what is the potentially best next point to sample in the landscape of this GP. And now you can see here now with one single card, you can see that the tuning is not great. So so far we're only one single context. Now we speed up the video a little bit, and we can see that the algorithm keeps basically driving one lap. The context is fixed because it's only one car. So we build the GP model and we decide where to sample next. After about 15 iterations, we can see that basically we reached a plateau. So in about 15 laps, we could find a better tuning that, as you will see in a second, is not, let's say, wobbling so much if you from a, let's say, performance point of view. Okay, you see here now the controller, you can see now that the car is not wobbling anymore. It has a let's say much better behavior. And when we introduce context now, so we let's say introduce a second car that is different from the first one, but we use basically the same GP with a different with a different theta. Well, we see that we don't necessarily gain much with respect to directly using BO without context. But then the advantages become more evident when we add more context, for example, a third and a fourth context. We can see that we can speed up the tuning procedure. However, be careful that this doesn't mean that we converge faster. This means that we start off directly with a better weight, and maybe we could be happy already with this setup that we have at the very beginning, or with just a few laps of training of the BO algorithm. Okay. Another example of, let's say, targeted exploration is related to this multi-agent example. Actually, this video is something that I did during my for my PhD. And let me introduce very briefly the coverage control problem. So in coverage control, you have a group of agents that need to cover an environment. Okay, and the area of the environment is not, let's say, not all points are necessarily equally important. We have a density function underlying the environment which tells which area are more important. So imagine, for example, that you have a group of drones that want to cover an area and want to prevent a wildfire. For example, where the temperature is higher, there is more likelihood of a fire, and so you will have to have more drones in this area with high temperature. And I mean, it has been studied quite a lot, this problem, but where it probably becomes, let's say, more of a, let's say, control problem is when we do not know the density function in advance. So we don't know which areas are, let's say, more interesting to explore. And so that's why we have, let's say, coverage control with active learning, where agents first start exploring the environment to sample the density function. And then when they know enough about it, they perform coverage. And so here you can see this example where the agents are, let's say, sampling the density function, and they're basically performing sampling in a probabilistic. They decide where to go basically in a probabilistic way. And here the two questions we had is that, first of all, can we allow for constraint satisfaction? As you can see, sometimes the agents can, also if they don't have simple single integrator dynamics, could violate their constraints. They could get out of the normal partitions. And also, can we have a better approach in exploring, let's say, the environment? And so what we did was, again, to take inspiration from Bayesian optimization. So we have an MPC, and the MPC allows to basically satisfy constraints. So we have our dynamics, and we require that our position is within the Voronoi partition, so we cannot collide with other agents. And then we add as terminal cost to the MPC the coverage cost. So this is called the locational cost from coverage control. That's what we want to minimize, minus a term that includes basically the uncertainty. And so we try to explore in a very optimistic way, where we are very uncertain, right? If we're very uncertain about a location, we will sample from it. And at a certain point, if we become more certain and we know that there's not a minimum, we'll go somewhere else. So basically, this term here basically brings together the coverage cost plus the exploration. And what we can, the properties of this algorithm is that we have constraint satisfaction. These are given basically by MPC, but also we can show that we converge to central configurations, and that we can learn the density function with some, let's say, epsilon accuracy. Okay, and then actually we also implemented this on hardware with multiple agents. And we have seen that comparing this approach, where we directly optimize basically the trade-off between exploration and exploitation in the MPC, leads in general to a much faster exploitation time. Okay, so with this, we're at the end already of the presentation. And so in general, we can see that learning-based MPC seems a very promising direction to explore. I mean, in the work that I show you today, I mainly show basically the feasibility that this basically approach works. We have some other experiments, but still there are some limited guarantees. There are some groundwork that has been done on learning-based MPC, but I think there is still a lot that can be, let's say, explored. We can still improve in the domain of computation, so to just try to develop, let's say, better solvers for allowing to, let's say, optimize for larger optimization problems. Of course, also the multi-agent direction is very interesting. So we want to coordinate among multiple agents, and it's, in my opinion, still to be defined what is the right direction to take also in how to solve the optimization problems for multiple agents. The other thing is that we need to simplify the tools that we are using for deployment. They're still very complex, and so it's very hard for people to adopt them, not only in research, but also if we think about industrial partners. And also to bring all these topics into, let's say, education, so actually how to teach this directly in our classes. With this, that's all, and I'm looking forward to your questions.